So is this a bad pattern to wear for video? Yeah, so my question was, are the exercises, I asked that at the office hour too, if they're in line with the material. I know there's a lot of material that probably there are no exercises on. That I know, because we can only do so much. But I'm a little concerned sometimes, and maybe there are exercises that the TA didn't realize that maybe it's material to come.
Yeah, perfect. That's it.
Or you felt it was pretty well. Yeah, the exercises are pretty well in line with the material.
Yeah.
Yeah? Like the ARL was talked about in the videos, right?
Yeah,
Today.
right.
Oh, okay.
I'm
Okay.
not sure that exercise is like covered all the material because you got lots of material.
Yeah, we got lots of material.
In
Yeah.
videos, we
Did
cannot.
you know that? You have lots
I'm
of
not
material.
Huh? I have lots of, yes, I knew that.
Too much.
Yeah, too much.
I just can't.
Hey, we cut it down. You guys owe me big for, right? Don't they?
The what?
You were on day 5 and then it turned out.
Yeah, I wasn't. No, day 6, and Allison and Johnny says, "Are you sure you kind of covered this much?" I said, "I'm only on day 6," and then I read.
Follow all the materials when Saturday and Sunday, because
Yeah. It is a lot. It is a lot. And today today is an overview. So there was a lot of, a lot of a lot of stuff done on the surface. I don't think there was that much depth today. It was like a lot of different things. That's my impression of the day. But anyway. Yeah, so let me make my list. So we're going to do problem 2, right? Yeah. So you guys now know which problem is on the assignment. So you can engineer the assignments if you all get together. Anyway, problem 2. I want to do exercise. I want to do day 2, like a leftover from yesterday. Day 2 exercise. Exercise 2. I want to do something about hypothesis testing versus confidence intervals. Because I think there's something there that I think need to clarify. I got to get the whole ARL story, I got to get it straight. Like there seem to be too many questions that show. Anyway, that's my list. I don't know what order I'll do them, but is there any other items, either from the online folks or the inline folks, that you want to add to this list? I think I addressed the H1 alternative this morning. There's lots of stuff on Google. By the way, there's lots of, on quality control, there's lots of stuff out there. But, the hypothesis testing is pretty fundamental. The whole idea of a null hypothesis, an alternative hypothesis, and there's lots of descriptions out there. The gist of it that I got is that the H0 is what you expect, is the norm. And therefore you want to know whether there's anything unusual, whether anything unexpected. So you get data and you see, hey, what I was expecting is not really true. I think the Earth is round, right? Is there any data out there that would tell me that it's not? I think there's no more data out there that tell me that it's not. But every day you see things like, you thought this, medically speaking. You thought that, you had to get rid of all your cholesterol. I'm showing my age. Well, not so clear. A little bit of cholesterol is good, And there's controversies and so on. Anything else on the list? Okay. So I've got 2 minutes to 4. You have 4 o'clock. Okay. So let's put an order to this. Let's do the old business before we do new business. So let's just do this one first. And let's do ARL second. Let's do problem 2 third. And then fourth, because this is not fundamental to being able to do the exercises and so on, but I think it's something that you should know. So I'll raise it last. Okay, so that's that. So moving right along. Is there a board in between? Yeah, no, this is it. Okay, so item 1, which is day 2, exercise 1. So day 2, exercise 2, exercise 2, right? Yes. Which of the following options are all, for which of the following options are all the definitions correct? Okay, so option 1, type 1 error is called beta. That's not right, right? You know that right away. Type 1 error is called alpha. Okay, we know that. Now, what is a type 1 error? A type 1 error, and this relates to ARLs too, so I will, let's do it in terms of the control charts. This is the center line. This is the upper control limit, the lower control limit, and the center line, okay? And a type 1 error is when you think that you think things are under control, and so everything looks good. No, you are under control. You are under control. Everything is good, but you get a false alarm. You get a false alarm. That in the area of control theory of control charts. That is that kind of error. But I'm confusing it by adding control charts at this stage. Maybe I should just stick to this question here. A type 1 error is so we have a little chart, right? In the video, there is a chart. Do you remember what the columns were? What were the headings on the columns? It's either H naught is true. Yeah. So H naught is either true or false, right? And if H naught is true, then you can get you can get a reject and fail to reject, right? So you get a reject and fail to reject. Okay. So if the thing is true and you reject, what kind of an error is that? That's the alpha. Okay. That's the probability that things is true, but you're going to reject. The evidence comes up, you're going to end up rejecting, but it really is true. Okay? And what I mean by relating it to the chart here is that H naught is true with the H naught in control charts is that everything is fine. That's what I expect. The base is everything is fine. Machines are running, we're producing defects, yes, but within a reasonable range, everything is okay. But maybe the thing is really not working anymore, but I'm still getting points within the lines. Just because I'm getting points within the lines doesn't mean business is good, because there's always an error alpha that things might not be good. I just don't know, But things are good, but I'm getting a false alarm. I'm getting confused myself too. Okay, so I get all of a sudden an X up there, higher than the upper control limit. Okay, all of a sudden I get that. I jump. Oh, something is wrong. But maybe it's just a false alarm. So what happens is you have to find an assignable cause. That's the proper name for it. We've used different words, specific cause, but in control chart, quality control, it's called an assignable cause. It means something looks like it's wrong, let's find out what's going on. And you search and you search and you search and you stop the line, right? You're not producing because you're afraid, but we can't figure anything wrong. And then you say, oh, you know what, it's been a half hour, we haven't seen anything wrong. Let's just carry on and see what happens. And then after that, everything is fine. Okay? And then you say, you know what, there was a false alarm. And we know a false alarm can happen. That's an alpha. Okay? And so what will this be? If it's true, then the probability of rejecting is that, but the probability of failing to reject will be 1 minus alpha. Yes? Yes? We're okay? Now, let's look at the other thing. H naught is false. Relating it to control charts, because that's where we're going, things have shifted. Something has happened. A machine broke down somewhere. Guy's not showing up for work, and we don't know about it yet, okay? So parts are being produced. Something is false. What is the error? What would be the error in this case? It would be beta. Where would it go? Bottom or top? Bottom, because I'm failing to reject, but the H naught is false. It's wrong, but I'm failing to reject. I think the null hypothesis is true. Well, guess what? You're making a mistake because it really is false. okay? And then here is 1 minus beta. It means that there you got it right, okay? So that's the alpha and beta. So the type 1 error is called alpha. This is called the type 1 error. Type 1. And this is called a type 2. Okay? Alpha is the consumer's risk. Have I talked about consumer's risks? Do you know what that means? You may know what it means, but I don't know what it means right now. Do you know what? Okay. But since the first one is wrong, I don't need to read any further. So right now, if you ask me what the consumer's risk is, I don't know. Okay? If you ask me what the power is, I know power is 1 minus beta. It's not 1 minus alpha. So that one is also wrong. So I can tell you the first and the third are wrong. I don't know yet about the middle one, but that was just fill in. Okay. The second option is alpha is the probability to reject H naught given H naught is false. So H naught is false. We get the wrong entry here, right? Yes? False. So the first one is false. Beta is equal to 1 minus power. That is true. Okay? Now, I don't know if I explained it. I don't think I have. I don't know. That is just a fact. That's just linguistics. Okay? Beta, we know what it is. There's something called the power of a test. And the power of a test is, okay, it makes sense. The power of a test is the power to be able to identify that I have a wrong, that my hypothesis is false and I actually reject it. So the power of a test is when a guy lies outside and it really means that something is wrong. If that power is like 0.99, then I'm sure there's something wrong. And if we can't find an assignable cause, we look some more. If we are told that the power, that beta for this particular situation, we calculate a beta of 0.0001, because our control chart is so amazingly, it collects 500,000 units every 5 seconds. I don't know. It just collects a ton of information all the time, so we know really where we are at. And you find something is wrong, something is outside of the control charts, there's something wrong out there, okay? This is too much of a fluke. So keep the line down until we find this, okay? So, beta is 1 minus power. This is the power. So we can put power here. Okay. Beta is the type 2 error. That's correct. Okay. So now we get to the third one. Alpha is the probability to reject H naught if H naught is true. Right on, bang on. Beta is the type 2 error, bang on. Power of the test is the probability to reject. This is a little tricky because it's 1 minus the probability to accept given that H naught is false. It's a reject given that, sorry. So this power is equal to P reject given H naught false, right? And that is, yeah, that's this right here, right? Given that that's there, this is the power, and it's equal to probability to reject given not is false, which is right there. So it's correct. So the third one has all three. Yes? So I think I wanted to spend a little more time because it's very important to really understand this and also understand it from the control chart, in the control chart's context. That means that you can have a false alarm, things are under control, but you have an entry outside of your bounds. That's possible, okay? And you also can have the other way around, which he showed in terms of circles this morning, okay, at noon, or whenever it was, 1:30, that you are showing points within the bounds, and yet things are under control. Are not under control, okay? Things have shifted. You should be getting an alarm, but you're not getting one, okay? Now that takes us to that's the first item. That takes us to the ARLs. So the ARLs, I'll leave everything here. I'll just imagine, okay. Alpha, do you know the normal, with three plus or minus 3 standard deviations, do you know what the value of alpha is? Nushin just mentioned it like it's a hard number, like pi, stuck in her mind. It's no, not 2 standard deviations. We're talking about plus or minus 3 standard deviations is equivalent to an alpha of what? No, 2 standard deviations is roughly 0.05. A point, no, try again. Point, okay, first of all, 0 point. We're talking about the alpha equivalent to plus or minus 3 standard deviations. 0.0. Okay, it turns out that it's this. Okay, that's what it is. Okay, this, if you take a normal distribution, a standard normal distribution with mean 0, right, and you want to know plus or minus, this is minus 3 standard deviations, minus 3 sigma, plus 3 sigma. Actually, it's plus 3 and minus 3 because this is a normal 0, 1, right? Right, this is a normal 0, 1. So if you want to know what is the area under the tails, this is too generous here. What is the area under the tails? The sum of the 2 tails? It's 0.0027. You were going to say something else? Okay. Now, I have trouble I have trouble remembering this number, but there's another number that you will see very frequently in this course, which is 1 over 370. It turns out that this is equal to 1 over 370. Okay. Now we have the probability of this being true and rejecting. So what we're saying is the probability of there being a entry that is outside of the limits, that's that alpha probability. So the probability of this happening is what? What's the probability? Things are under control, but you see a point outside of the plus or minus 3. This is plus or minus 3, okay? Yeah, outside of that. It falls outside of the bounds. It finds outside of the upper and lower control limit. That would be a reject, but is it possible that this thing is still under control? Nothing happened. It's possible. And what would be the probability? Alpha, which is? 1 over 370. So if you run this thing for, so if you're looking at a year, how many of these false alarms do you expect? Let's say you run them every hour. Let's say you get a sample every hour. Every hour there's a sample. So how long would it, on average, how long would it take for there to be a false alarm? 370 hours, right? 370 hours divided by 24, I don't know what it turns out. 370 divided by 24, you get the number of days. What's that, 10 days? 15 days? Something like that? A couple weeks, between a week and 2? So every week or 2, 15, thank you. So every 15 business days, every 3 weeks, okay, you can expect a false alarm. So if you're in the business and you see an X out there, you don't necessarily get that excited that there is necessarily something wrong as long as you see one on average once every 3 weeks, right? But when you see one, it doesn't mean you can do nothing, right? But you should know that the control chart is designed in such a way that on average you'll see a false alarm every 370, which means the ARL naught, and that's the ARL, the average run length, means the average number of hours, if you take number of samples, the average number of samples before you see an alarm, given that things are under control, everything is fine and dandy, nothing went wrong, is still 370. Okay? Yes? I'm doing a little bit of teaching here, which I'm not supposed to do because there's little videos, but I think that there's nothing wrong with that, I think. Okay? Because it's very fundamental. Okay? This stuff is very fundamental. So if you don't understand this stuff, you get stuff and this lost on that stuff, everything else is, well, what's going on? So ARL naught is 370. Okay? Now, we have control over that because this is designed with 3 standard deviations. This is our control. We control that. We choose, in the control chart, we choose that. We could have picked 2.5 or 2 or 1.8 or whatever it is, but the industry, especially in North America, has decided that plus or minus 3 is the industry standard, which means people are willing to live with a false alarm every 370 days, and that number 370 is very commonly known, okay, in quality control, okay? And that's the end of the road, okay? But the question now is what is beta? Now, right now, the only way you can calculate beta is using Minitab. I think tomorrow's videos, it will show you that you can develop a little analytical expression for it, and you will not need Minitab anymore. You can just plug that into Excel. Okay, but right now, what you have to do is you have to go to power, sample size, and you do Z-test because you have enough data. You specify something very, very, very important. In Minitab, you have to go to options button within that power test and change the alpha to 0.0027 because the default value is 0.05. And if you keep that 0.05 in there, you'll get the wrong answer because we assume plus or minus 3 or whatever the question tells you. Okay? So this is very easy to forget. And yeah, I wish they had a default of 0.0027, but they don't. So they have a default. So it's very important in Minitab, when you do the power sample size, you go to options, change your alpha to 1/370 or that number. It asks you for sample sizes. So you can specify what sample sizes you provide. By the way, also a Minitab quirk is that the separator between numbers is sometimes different in different parts. Sometimes it's a colon, sometimes it's a space. Sorry that I ran into this. It's a space, I believe, commas I don't remember seeing. Maybe there are commas sometimes. So the separators between numbers is I don't know, find out. Okay, so you specify the different sample sizes. You specify the difference. Now here's another big deal. A big deal is that when you're talking about beta, you need to assume what shift do you suspect took place. You can't just calculate beta. Give me like alpha. Alpha was unconditional. 1/370, that's the end of the show, right? You have to specify, if you want to know the probability of rejecting falsely, you got to tell me what you're rejecting. How much do you think it shifted by? What's your normal? My normal is 10. Mu is equal to 10. My normal mean is 10. Well, if you want me to calculate beta, I can't just calculate beta without knowing, the chances of this being rejected, if it changes from 10 to 10.00001, I'm going to have a heck of a time detecting that difference statistically. But if you tell me that it doubled, then I have a good chance of finding out, right? If you're watching a line, right, and you suspect something is wrong, you want to know beta, and you go to you have to calculate. You say, well, what am I suspecting? You know what? I think the air conditioner may have turned off, and if the air conditioner turns off, on average, temperature goes up by about 5 or 6 degrees in the summer, and that would make the mean shift from 10 to about 13 or 14. And let me see if that's what might have happened. And then you put in your 13 or 14, you calculate a beta. Okay? So if you want to, and then once you calculate a beta, now you might say, what the heck do I do with that beta anyway? Okay? What you do with that beta is just like this guy was 1/alpha, okay? ARL1 is how many, so we forget about this guy. Things have shifted. I suspect something has shifted. And now I start to watch these zeros. This is when I suspect it might have happened. I see the first 0 there. No, I don't know. I don't know when this started, okay? But let's say God knows when it shifted, all right? He knows when the air conditioner turned up. I don't know yet. In reality, okay. And then I see a 0. I don't know if it's a 0 because I just see an X, right? I don't know whether it's a 0 or an X. But so let's just make it X. But somebody told you, you now know, let's assume for a moment that something changed. The air conditioner conked out. And you're on your merry way, and you're seeing X's. The question is, how long do you think you might have to wait before you see an X going above the line, given that things are not under control anymore? That's what the ARL1 is. The ARL1 is the run length how many good x's do I have to, if things really shifted, how many good x's do I have to wait for on average before I actually see an alarm? The thing went out of control right there. That's the reality. Okay, somebody pulled the plug. You know, there's a guy sitting by the air conditioner. He pulled the plug. He said, hey, I wonder how long it's going to take for them to find out. Okay? Well, if they have a lousy, badly designed control chart, it may take them weeks, right? If they have a well-designed control chart, which tries to minimize ARL, they'll find out sooner. So one way to do a quality control on the quality control is to go and break something and then see how long does it take for you to find out, okay? Well, it's good to do that with simulation. You can do that with simulation. Later on in the course, I do that. I take things out of control and I see, hey, how long does it take to find out, okay? So ARL1 is equal to, just like this guy was 1 over alpha, this is the probability. Now we're looking at the probability of rejecting given that it's false. We want one that is outside, right? When it's out of control, we want one. So the probability of rejecting given that it's out of control is what? 1 minus beta. That's the probability of rejecting. That means the point is outside of the limits, given that it's actually out of control, that it's false. Okay? So we want, instead of 1 over alpha, this is the probability. So if whatever that probability is 0.0, if that probability is 0.5, right? If the probability of, once it's in control, is a probability of 0.5 that you're either within or outside, right? Then how long do I have to wait on average before I see a false alarm? No, it's either it's 0.5. It's 0.5, so it's 1 over 0.5, 2. And that makes sense because half the time it's going to be in, half the time it's going to be out. Right? So 2 is what I, on average, would have to wait. Right? If my probability of this is 1 minus beta would be 1, beta 0, then I would find out right away. If 1 minus beta is 0.3, then it's 1 over 0.3, that's 3. If it's 1 over minus beta is 0.02, it'll be 50. I don't know, is it? Something like that. Okay, so ARL1 is equal to 1 over 1 minus beta. Okay, and you calculate beta right now from Minitab. And there you go. Okay, I think I have spent enough time on ARLs. Is there any question on ARLs? Yes.
So about type 1, so
yes.
when we are alpha is beyond rejecting 2.
Yes.
As long as alpha is smaller, it's better for us. That means you are not rejecting something.
Correct. Yes.
So if the alpha will go be smaller, the ARL will be bigger, right?
Yes. Correct.
As much as the ARL is better,
yes.
bigger is better for us.
Yes, that means that's right, because you don't want a false alarm. If some big boss manager says, I don't care how you run things around here. Okay, I want to only see a false alarm every 1 out of 1,000 hours. And he dictates that. Then they're going to give him a control chart with plus or minus 10 standard deviations. And then he comes in, so how come we're doing business different than everybody else? Well, you told us 1 out of 1,000, so I guess it won't be 10. It will be bigger than 3. I don't know how much it will be. Maybe it's very easy. Anyway, okay, it'll be bigger. How come? Well, you told us 1 out of 1,000. The industry standard is 370. I said, oh, I didn't realize that. Okay, go back to 370. Okay? So, but you're right. We want it to be smaller, but the smaller, if we make it ridiculously small, then that has, so your question is, why don't you make it 1 over 1,000? Because then you would never detect an out-of-control situation, right? You would have very few false alarms, but at the same time, everything would be hunky-dory every day. You would never know anything is wrong. So it's a matter of trade-off between alpha and beta, right? Alpha has been cast in stone. The way this works is like this. Alpha is cast in stone. You can change beta by changing the difference that you're looking for, the sample size, and those are the only 2 things. The change in mean that you're trying to detect, and you say, look, I'm only trying to detect a big change in mean. I'm not going to try to detect a 0.1 change from 10. I want to know when it goes to 12, okay? Because I don't want us to be chasing. But as the process gets more and more stable, and as you get better, that's what Six Sigma is all about, right? As you get better and better, you can get better and better at your quality. But initially, when you start in phase 1, things are a mess. That's my excuse. If this course is a mess, it's because it's the first time that we're teaching it. So we're in phase 1, guys. Yes.
There is a question.
Yes.
Does Minitab power curve calculation assume the process is out of control?
Okay, Minitab beta is, okay, it's correct. It is for out of control because the power of a test is defined as the H not being false, which means that the system is out of control. It calculates the power. Power is related to beta. Beta is related to out of control. There are no calculations to be made for in control because in control it's alpha, and alpha is 1 over 370 for 3 standard deviations. There's no calculation. The thing that is hard to calculate is beta for out of control conditions. In control, there are no calculations, significant calculations. Yeah. Does that answer? I hope, yeah. Yeah.
When plus minus 3 changes, what happens to...
Yeah, then your alpha has to change, right? Then you can change, then the beta will depend on alpha, right? Because that's why you have to go to the options within Minitab. This beta is a function of the sample size n, the difference that you're trying to detect, and also of alpha. Those are the 3 inputs. Okay? So alpha is related to the 3, right? To the number of standard deviations. I don't know if you can still see on the, yeah? Yeah, does that? Okay. Now, I know these things are all new and they take a little while to internalize, and there's nothing, you know, really all that hard. It's just that it's all new and a lot of pieces in a short time, okay? Okay, so any other question about ARLs before I move on?
No.
Okay, and here we're okay also? Okay. So, so the third item is problem 2. Okay, consider, and so I'm going to, you know what, let's have this up. Okay. Consider an X-bar charge with 3 sigma limits, so we can use everything we talked about, used to control the manufacturing process. So we got one of these bar charts. The in-control process parameters are mu naught equals 10.3. So we're given a mu naught, that is the in-control mean of 10.3. That's what we want. And we experience a standard deviation of 1.6. That is our current estimate of the standard deviation of our process. Okay, that's what we currently experience. That means each piece that we're doing is normally distributed. We assume normally distributed. Mean is 10.3. And then we have plus or minus, you know, we have this standard deviation, so we can do anything with that. Suppose there are 2 quality control options. Okay, there's option 1, O1, is to okay, we had a mishap. We were behind the moon, and we lost connection. Okay, so so the issue is, I don't know where I was when it crashed. You caught it pretty fast, right?
Within a few minutes.
Okay, so just going back to problem 2. Problem 2 is we have 2 options. We sample. We take 5 samples every hour, or we take twice as many every 3 hours. And the question is, which one gives me, well, I would like to think which one is better. That's what I think he was going. But then he stopped me with part A. Which option gives the higher in-control ARL? And I'm confused. What do you mean in-control ARL? What's the in-control ARL? What was that? Yeah, it's one, and what is it with 3 standard? He told me it's 3 sigma limits, right? So with 3 sigma limits, what's ARL? What's the in-control ARL? The in-control ARL is ARL naught. That's the in-control ARL. So what's the in-control ARL? 370. It's 370 no matter what, how often I sample. That's the chart. There's nothing to talk about. So I feel like saying, what are you talking about? Okay, they are the same. Okay, there's no, it's a trick question. Which option gives the higher in-control ARL? They're both the same. They have the same control ARL, which is 370. That's it. What do you want from my life? B, which option gives the lower out-of-control ARL when the process mean shifts to this much, by so much? Okay, so now what we're going to do is we just said that we can go to the power sample size in Minitab, right? Yes, and we can specify n equals, actually we might as well do them at the same time. So we go to Minitab, okay, Minitab, power, and, by the way, you know, it took me a while to find that in Minitab because I was kept on looking for the, there's a curve, operational curve, but it's the same information as in the power curve, okay? The power and sample size, I think it's called, under data, under stat. Stat. Does anybody have Minitab open here? Okay. So I think you go to stat, and then power, curve, and sample size. Power and sample size? Yeah, power and sample size. And it doesn't need any data. It doesn't need any large amount of data. It just needs a few parameters. It needs to know what n, the sample size is. So I'm going to put in 5 and 10. Okay. It's looking for what shift. What's the next? What does it ask for next? Underneath the sample. I think difference. Difference? Is that what it's called? I'm talking about part B, and I'm talking about Minitab. If you go to stat, you have Minitab open now? Not yet. Okay. No, fine. While she catches up, do you have Minitab open now? So you go to stat, power and sample size. Do you see that? At the bottom. It's all the way at the bottom. Okay. You open that up. Power and sample size. Oh. Then Z, one sample Z, because we assume we're dealing with only one quantity that we're charting, right? And we have lots of data. Okay, we have lots of data. Okay. Now, okay, this is a moot. It's a point, but it's a very important point. When we're talking about statistics like day and 1 and 2, we make a big difference between T and Z. You know, if we're small, it's T, if we're big, it's Z. You know, when you enter quality control, it's almost like the T distribution is forgotten, okay? And Z is what's used. Normal is assumed everywhere. Because I think people in quality control, they just they don't want to make life, so there is an element of that. The people who are practicing quality control do things very much by the book without really realizing what's exactly happening, okay? So they assume always normally distributed. I had a lot of trouble with that, and I was going to change. And I was told that there are people who are sticky about the T in quality control, but they're very few. So I don't want to make your life more difficult. So we're going to assume even 5 is big enough for normally distributed. We're going to go with Z. So we go with one sample Z, window, right? In window, it asks you for sample sizes, correct? So you put in 5 and 10. It asks you for difference. Is that the next one? You put, what's the difference in this problem? Let's read it. The read was that which option gives a lower out of control error when the process mean shifts to 11, to U1 11? So what's the difference? What difference are we trying to detect? 0.7. So the difference delta is 0.7. We don't have to put in the third one because it only needs 2 out of 3. But we do have to go to the options and change the alpha to 0.0027. It won't take that in there. I tried that. Thank you. I had to do it on my calculator. Okay? They changed that 0.0027? Yeah. Yeah, so at home, I really urge you to, there are technical reasons and there are pedagogical reasons for me not having a computing. The technical reason is that displaying things on a screen looks horrible on video. And the pedagogical reason is because I do want to keep this tutorial at the fundamental level, at the logical level, and not at which button do I press necessarily. If you need to press buttons, you can press the buttons, okay? If you have questions, I'll take them. So now you press the button and you get a graph, right? Yes? Ignore the graph. Go to the text window. Probably the graph is covering the text window. You need to move the graph, and there you see the power, right?
For size of 5, it says power 0.0216.
Right. Now, yes. So now, whoa. What do we need? We need 1 minus beta.
That's power.
That's power. So what we need really is, for option 1, what will it be? The ARL1 will be what? Will be 1 over 0.02 blah, 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 which you can do. Somebody does it. I don't know what it turns out to be. Actually, I do. It turns out roughly 0.02. 1 over 0.02, not 0.2. Over 0.2 would be 5. Over 0.2, it's roughly 46. Okay, so it's roughly 47. Okay, just rounding up, because as mentioned at the office hour, ARLs are integers by nature. It's the average run length, the number. Now, because it's average, you're going to get a decimal. But in real life, when people talk, it's 47. Okay. So that's the average run length you get there. What will be the average run length for here, for this out of control situation? 1 over whatever, 0.05, something. I get roughly 19. I get 1 over that, roughly 19. So what we're facing is that option 2 gives you a much lower ARL. But what's wrong? It's 3 hours. So if I do it every 3 hours, this thing runs out of, you know, I have to see 3 hours. So I could be I would have 19 times 3. How much is 19 times 3? So the ATS, let's get that right. Let's get that terminology in there. ATS is equal to H, which is the interval length, right? The interval length, which in this case would be 1 times, so it'll be 1 times 47, right? So it's 47 hours. It takes 47 hours to get a false alarm. Yes?
Question.
Yes?
For same ARLs, you could have different ATSs due to different sampling intervals. How is this
Whoa.
your choice?
Okay. Yes, okay. So is she okay on ARL? She's okay on ARL, right? ARL is number of samples. Yes?
I don't know what she's
You don't know.
I'm just reading the question.
Yeah.
Sorry.
Okay. You all have access to the chats. Okay, let's, because Joanna is doing this right now, but do you have access to the, because you're not watching the stream. Right, because why should you watch the stream? You can see it 5 seconds earlier. Yeah, so let me see the question again. Question for same ARLs, you could have different ATSs. Yeah, but yeah, it's a true statement. For what she is saying is true. For the ARL is only the number of samples, the average number of samples. Okay, but the ATS is the time to signal. It's the number of hours before I find out something is wrong. So if I have to wait for 47 samples, but I am taking one every hour, then I have to wait 47 hours before I see that something is wrong. So when I detect an X, on average, this stuff has been wrong for the last 47 hours, and I just didn't know about it. Okay? So before I jump to the conclusion like I did before, this is probably a false alarm, it happens every 3 weeks. It's not an excuse. You better jump to it, because you also know that if you see one out of bounds, it's probably been wrong for a long time, as long as you're ARL. And your ARLs are very often in this kind of, the quality control is not perfect. Okay, it's all statistical. And so for the other one, you're going to get an ATS, which now you get 19, which is lower, but you got to wait. The number of hours you got to wait is 3 times 19 before you see. And this is equal to 27, what is it? 57. So this is 57 hours. So the second option gives you you have to wait on average 57 hours to detect. The first one gives you 47 hours, so you pick option 1. Did I answer the lady or the guy? Or
he or she will let me know, but there's another question.
Okay.
When sigma is given as a process parameter, example 1.6 in problem 2,
Yes.
is it the standard deviation
Yes.
of the mean distribution, i.e. sigma over square root n?
No. The answer is not. The sigma that is given is sigma of the data. So the mean of the data is 10.3, and the standard deviation is 1.6. When Minitab, it's a good question. When Minitab asks for when we talk about standard deviation, so half this course is language and half this course is math, okay? So there's convention in language. When you talk about standard deviation of a process, you're talking about the original data. You're not talking about the average. You're talking about the original data has a mean of 10.3 and has a standard deviation. The original readings have a standard deviation of 1.6. If you're trying to build a confidence interval or do hypothesis testing or do control charts, when we will actually build control charts, which I don't think have done yet, then we will be using root of n again and applying that to the sigma naughts that are given. So it's definitely the standard deviation of the data, of the population, if you like. That answers that. So as just as a matter of format, I think it would be useful if we sort of have one person turn on the stream just to watch the chat. So you don't have to look at the picture, but just so you can see the chat and somebody asks, because you will be much more in tune with what the person is asking than Joanna, right? So I think we still have a number of days to go. So can I take a volunteer from you? Yeah? So it's a matter of turning on the stream. Is that hard? You can do that, right? Yeah, can you do that now? Can you, yeah, in the whatever 15 minutes we have left, we can try this out in.
He asked, so sigma calculated from R bars populated SD, question mark?
Sigma, yes, correct. Right, so the way you would derive a sigma, like where did this 1.6 come from? This 1.6 came from the company being in business for a long time, it doing an R bar chart or an S chart and measuring the standard deviation. Initially, when an assembly would start, you would run it for many, many runs, take many, many samples, as many as you can, to establish your best estimate of sigma. And that would be the population sigma. Correct. Yeah, you're on? Yes, do you have a question?
I know you said it before, but
No.
in the video, I said that you calculated first ARL as 1 over alpha, and then in the next slide, it was ARL as 1 over 1 minus beta.
Yeah, so what I forgot to put is I forgot to put the subscript. I figured from context, the context was that we were talking about in control conditions, and then we were talking about out of control conditions.
So that's the only difference between 0 and 1?
Correct. There is no other difference. Okay, yeah. It's a mu naught, a mu 1, the same kind of lingo. So that is problem 2. Which option do you prefer? Now there may be other considerations, okay? There may be other considerations. I should tell you that the general industry practice is to sample frequently and small. That's a general preference in industry, is to use sample like 5 very frequently. Now, there are some conditions under which they sample every unit. Okay? They look at every unit. And by the way, do any of you have any experience? That means including the online. Are there people in the group who have some kind of online working experience with quality control through PEY or previous lives or whatever? Okay, because I was surprised. I had the simulation was developed by Caroline Busby, and she worked for a candy factory, and they sampled and they tested things, and if things were wrong, they would stop the production, and it would big investigation, a big detective work starts. I mean, that's where the really interesting quality work starts, is to do a detective work. Who's the culprit? Who did the who did the crime? Right? What's the sort? Things have gone off, but what's changed? What happened? Okay, and then you start a whole investigation. This is just the detection. This whole course is about how you detect, given all the uncertainty. First of all, how do you set up a control chart, and how do you detect that something has gone wrong? Yes.
And how do they test the candy? They eat it?
I think so. I think she told me that. She gained a lot of weight.
A lot of candy.
I think that was part of it. The other thing that was let's look at this. Would you always do that? It might be expensive to do every hour. It might be a lot cheaper to do every 3 hours 10. Okay, you might have to do something that costs money. So in the area of quality control, there are 2 ways of answering these kinds of questions. There's sample sizes in terms of the limits, in terms of the things that you can play with. The frequency, basically the frequency and the sample size. Those are the 2 things we play with. Okay, one is based on ARL and ATS, and that's the introductory kind of way of doing it. When you get really sophisticated, it's based on all the kinds of costs. So it's the cost of sampling and the cost of stopping the production, the cost, all the costs involved, and then you determine stochastically which one gives you the lower expected cost. Okay, but we're not doing that in this course. Okay.
Someone said they have 9 years in QA.
Oh wow! Okay, so if you have that and you have a question or you have a comment, or that would really be nice to hear from. Okay, if you can share your experience, that would be a good thing to hear. Not right now, whenever you choose. You'd be welcome. Be welcome. Okay. Now I have one more item, which is we did this, we did that, we did this. Is any other question regarding problem 2 related? Okay. The next thing is actually not as interesting now. The next thing has to do with hypothesis testing versus confidence intervals. Okay, it's a bit dry, but what the heck? So in hypothesis testing, we talked about you have an H naught. You have a null hypothesis, which says that, let's say, that the mean is equal to 20, and an alternate hypothesis that says that it's not equal to 20, and you then collect a sample, x equals 23. Okay, that's a sample you took, and you want to know, and you also have some kind of a standard deviation of the sample. Okay, and you have the sample size. Okay, but these are numbers. It's not important right now to know what those numbers are. So the way hypothesis testing, there's 2 ways. I think we talked about this yesterday. You can take the shortcut method. The shortcut method is you do right away z is equal to x bar minus mu over s root n. So that is 23 minus 20. So that's 3 over S root n. And then you compare that. Then if that is larger than Z alpha over 2, if it's inside inside minus Z alpha over 2 or plus Z alpha over 2, then you fail to reject, okay? Because you expect the area, then it's in the middle of the distribution. And if it's outside of either one, then you reject. Yes? That's the shortcut. That's the short way. The little bit longer way, you don't standardize. What you do is you ask, is X bar between mu plus Z alpha over 2 S over root n and mu minus Z alpha over 2 S over root n. So this is a number. This is 23. And this is 20. And this is 20. And these are all numbers you can pick up. You're given S, you're given root n, you can look up Z alpha over 2. It's either inside or it's outside. Notice the similarity. Here it's standardized, so you're just looking between here. Here you're saying, hey, is this X bar 23 outside the realm of what we expect, outside of the reasonable? Reasonable, if you're in fact right that the mean is 20, then you would expect X bar to be somewhere between this and that. If it's between those two, you fail to reject. If it's outside, you reject. Yes? Okay. So that's yes?
When we set up the bar and R charts, do we use the standard deviation of the samples or the factors table that is in the book?
I don't know what the factors table in the book is.
Oh.
Factors table? No, so the question was, do we use?
When we set up the bar and R charts, we use the standard deviation of the samples or the factors table that is on the book.
Okay, so let me answer that question. I think today's videos and the exercises ask you to use Minitab. Like if you need to do a control chart, you just go to the Minitab and you put down in, and it gives you the in control, out of control, and you're just letting Minitab do all the calculations, right? Tomorrow, when you see as videos progress, we will do more of the what's inside the box, what's inside Minitab, how is Minitab doing that, and then you will need some of the numbers. There is I believe it's called the factors, the one with the D2. Can you just ask, does it have, well, she can hear me. Does it have the D2? No answer? Okay. So there is a table in the back I normally don't like to go to that table. I like to go online and see where I can find those numbers rather than looking in the back. But
A2, D3, and D4.
Yes, it's got a lot of A's, a lot of D's. It's got D2. It's got many different A's and D's across. Right? Yes, we will be making reference to that table. As of today, you use Minitab. As of moving forwards, you may need to refer to some of those factors. You can get them online, or there's Minitab forum, which has a lot of these numbers as well. I tried to not use the table, but I've had to use it once or twice. Okay, that's the only table that I have gone to in the back. Yes, so I hope that satisfies that. So back here, when we go confidence interval. When we go to confidence interval, what's the probability, by the way, that that X bar is between these here? If U is equal to 20, what's the probability that this is true? What? Yeah, I think it's 1 minus alpha, right? Alpha is so the probability is this being true is like 99.99. It's very high. It's 1 minus 0.0027. If we, or with a 95, it's 95. It's 95%. The problem with a Z alpha with alpha of 0.05, yes, a 95% confidence. So it's 95% sure that this is true. You can do a little bit of a little algebraic manipulation of this, and you can convert this same expression, by subtracting x bar and mu from every one. If you subtract that, you're going to get minus, well, I'll leave it as an exercise because you can convert this very easily. This is equivalent. Well, let's do it. It's not that long. If I take away, it's minus x bar minus z alpha over 2, s over root n, less than or equal to less than or equal to minus mu, because I'm subtracting both minus x bar and minus mu, less than or equal to minus x bar minus z alpha over 2, s over root n, right? And now, if I just change the signs, if I multiply everything by minus 1, then the signs will change, right? And I will get x bar plus z alpha over 2, s over root n, less than or equal to mu, less than or equal to x bar. Sorry, this is, oh, I think I messed up somewhere. One is, oh, this is plus, yeah. X bar, and these have to be changed now. X bar minus z alpha over 2, s over root n. And what is that? This can all be computed. Mu, in confidence intervals, we don't know what mu is. We don't suppose a mu. We just ask, what is the possible range for mu based on this x bar?
No, but it's in the hypothesis as well.
But in the hypothesis, there is a 20, but there's no 20 in the confidence interval. The confidence interval doesn't use this 20. It only uses the x bar. This guy says, I put a stake in the ground. I think it's 20. And we check, is he right or is he not?
Yeah, but if you use the confidence interval to prove your hypothesis, then...
But no, what I'm saying is, if you notice, there's a subtle difference. Here, the interval, the interval is mu minus mu plus. And in the confidence intervals, it's x bar plus and x bar minus. So the confidence interval and the hypothesis interval are not the same. And some of you apparently in the problem did make the assumption that, and I was always, as a student, I always thought the two were the same. Okay, I always thought, I don't know, hypothesis testing is just a confusing version of confidence interval. Confidence interval I understood. Okay, simple, straightforward. Hypothesis testing seemed like a mathematical invention. Somebody was trying to confuse me. Okay, but now, many years later, I realized that they are different. Okay, in hypothesis testing, you make a stake, and that stake, that hypothesis counts in the calculations. In the confidence interval, you don't make a stake. You just say, somebody asks you, what's mu? I said, I don't know, but I can tell you a range, and that range will just use x bar. And I'm 95% confident that mu lies in there. Whereas confidence interval, the guy, he's stepping out he's saying, it's 20. And then we say, let's see if you're right or not. So there is a difference between the two, and there's a difference between, yes?
There is, but it's equivalent.
Well, but you can't do a confidence interval test using these values. Conceptually, there is a difference. Yeah? Algebraically. Okay, look at this, think about this, and tell me if you still think that's true.
Personally, yesterday, what I did was use the confidence interval, and I realized that it wasn't in the range, so I failed.
Yeah, but that's not, I don't know if that's computationally correct. Okay, I don't think it's computationally correct. So it just took up some marks. And he asked me because of that, and a number of people did that, to cover this. Okay, it's 5 o'clock.
Okay, we have one last
Yes?
question that's unrelated.
Oh, Joanna, do you see the question? Huh? Joanna, can you help her out?
It's a YouTube live link.
Oh, it's a YouTube live link.
Yeah, if you go to Portal, there's a link in there to the live.
Yeah, so at the expense of taking a minute or two, I just want to have it sorted today, to have somebody do that. Yes,
How do you hand in problem 1, and can we screenshot the graph?
yes. You can turn off the volume, yeah. Okay, yes, the answer is yes. If you need a graph, you can just cut and paste into your answer sheet.
And how to hand in problem 1?
You hand in on a sheet with this, you scan it. I mean, the same mechanism used today. You prepare a piece of paper. How you prepare that piece of paper, you're allowed to cut and paste from Minitab. You need to answer the questions. Okay, you can't just take it all from Minitab. You need to answer the questions. But as long as you've answered the questions, the fact that the graph was produced by Minitab is fine. Okay, this is not an exercise in drawing. So that's it. Anything else?
She says she has a question about yesterday's video, but I think that's.
Yeah, let's talk. Okay, I don't want to drop those. It's definitely, okay, this is a good point. Anything that we have covered until now that anybody has a question with goes on my list. It might go on the lower priority, but I will have a outstanding questions list, just like I carried over exercise 2 from yesterday, especially if I think the question needs to be answered. There's some questions which I can quickly answer, okay? But anything that takes any time, I will add it to the list. So please suggest it at tomorrow at any of the opportunities that we have. Make sure you tell us roughly what the question is so we can take it up. Okay? Thanks very much. Good night. All I need to go is to my office and press distribute to students. Problem 1. Yes.
Will we get assignment marks as we move forward?
Will you get what?
Assignment marks as we move
Yes, okay. So the question is, will you get assignment marks as we move forwards? Okay, the plan is like this: to follow the practice that we started today, to have marks back before Tuesdays by Thursday morning, we had the marks back, right? So it's like 24 plus, okay? We plan to continue that. The only thing is I asked the TA to mark the Thursdays before Friday, sometime Friday during the day, so at least you have an n equals 3 to determine whether whether you want to stick it out or not. Okay, because the Friday is the drop date. So I want you to have at least 3 marked assignments so you can make a decision. Okay?
So now marks are off already?
Marks have been distributed in your email. Has anybody received them? Huh? Yeah, the first one. That's the only one. Yeah. Yes. So I have been. So I've been told that I shouldn't do this.
Okay.
I know it seems weird.
I'm not in the course anyway.
Oh, no, you're the QQ. Oh, you dropped it?
They forced me to.
Huh?
Because I have 10 courses already.
Oh, I see. Okay, Joanna, what do you say? He's not in the course. Are we still videoing or?
Not
Okay.